Hello, Mr. Munyon here with activity 31-1, the sum of the interior angles of polygons. Hopefully we already know what the sum of the interior angles of like a triangle is, but we're going to focus on the other polygons like quadrilaterals, pentagons, hexagons, heptagons. So hopefully you know the names of the polygons up to 12-sided figures. If not, you might want to go review those. You do need to know the names of shapes up to 12 sides because we're going to be using them obviously here, and you may have some word problems that expect you to know the names of all of the polygons. So our goals for this lesson are to make sure that we have a formula to be able to calculate the sum of the interior angles of any polygon, and then go ahead and use that formula to determine either individual angles or the sum of them. All right, so polygon we know is a closed plane figure made up of straight lines that do not overlap. We also know what interior means, so we should have a pretty good idea of what the interior angles of a polygon, just each angle on the inside of a polygon. Below it asks us to see if we can take some shapes here. There's a couple other pages that I've got some information written on. It wants us to investigate and see if we can start recognizing some patterns. So on a triangle, we're not going to do these angles here, but there's one on the next couple of pages. We know that the total of the sum of the angles is 180 degrees. There's a proof earlier in the book about where that came from, but we know that if we had like 100-degree angle, a 50-degree angle, the last angle would have to be 30, and there's only 3 angles, so we don't have to worry about this one. On a quadrilateral, if we were to look down here at a quadrilateral on the next page, we would add up all of the angles, and on the example that they gave us, they add up to 360 degrees. I do have a pentagon here that we looked at. I went ahead and actually measured these and rounded to the nearest multiple of 5, just because it wasn't that accurate anyways. And I got 540 degrees for this one. So I'm not going to fill in all of those, but there's only 5 of them. And we did get 540 degrees if we were to measure each of the angles and add them up to get the total. It says compare your results with other groups. What similarities you notice? Well, even if we looked at other polygons, each triangle we would get the same thing, each quadrilateral we'd get the same thing, and each pentagon we'd get the same thing. So each type of polygon has the same measures. All triangles have 180 degrees, all quadrilaterals add up to 360, and all the pentagons added up to 540. So we're going to conjecture about the sum of the measure of angles of each of these. So triangles have a sum of 180. That's what we noticed if we were to compare several of them. Quadrilaterals have a sum of the interior angles of 360, and pentagons have a sum 540 degrees if we added up the interior angles. Okay, so then scrolling down, let's look at the 4th page on here. Use auxiliary segments to determine a way. So this right here is the instruction that's going to help us start to do the formula. To measure, or to predict and verify the exact sum of the angles of any quadrilateral and any pentagon, describe your method. Okay, so up here it says use what we know about triangles. All right, let's do that. So let's look at this shape right here. There are a few different ways I could try and break this up into triangles. Like if I was to do something like this and something like this, you'll notice I get 1, 2, 3 triangles. And I know for a fact that the sum of the interior angles of a triangle is 180 degrees. So if I was to add up this angle here, this angle here, and this angle here, I know that those 3 that I just marked have to add up to 180 degrees. Okay, let's look at triangle 2. What if I took this angle here, this angle here, and I'm just going to use 2 arc marks even though it's not congruent to that other one up there. And this angle, I'd know that the 3 I just marked on that one would be 180 degrees. And same thing with this 3rd triangle. If I looked at this angle, so I just continue it on, this angle here and this angle here, you'll notice that what I've just identified are the 5 angles of the pentagon. So if I use what I know about the angles of the triangles, I have 180 degrees for the first triangle, 180 degrees for the second triangle, 180 degrees for the third triangle. I have 3 triangles that have 180 degrees. Interesting, which means that I can use what I know about triangles to very quickly figure out the sum of this pentagon without actually having to measure it. Because I know that each triangle has a sum of 180, and when I add these angles together, they just equal one of the angles on the pentagon. So it doesn't matter that, this angle might be different than this angle over here, because when I add it together, it's just going to be one of the angles of the pentagon. And together, even if I have to use 3 or 4 or 5 different triangles, all of those angles are going to add up to be one angle of the pentagon. So obviously I can just add them together. 180 plus 180 plus 180 does give me 540. Does that work for other shapes? Yeah, triangle. There's already a triangle that's 180 degrees. What about this one? Well, you pick one vertex here and you draw a diagonal until you're done with triangle. And you can do them all from one vertex. Let me go back up to this pentagon just to make sure you guys understand what I'm talking about here. So you just pick one vertex and you go to any non-adjacent vertices. So this vertex is adjacent, there's already a line there, but this vertex is not adjacent, so I can draw that diagonal. This vertex is non-adjacent, I can draw that diagonal. This vertex is adjacent to this one, so I don't draw that one, and I end up with 1, 2, 3 triangles, and just like the other pentagon that we already identified, 3 times 180 does equal 540 on there. For this one, there was 2 triangles. 2 times 180 equals 360, and that is what we got for that other one that we checked up here as well. So we also got 360 for that one. So it seems to be there is a method that we could use to solve for the sum of the interior angles of any polygon using triangles. So it does say describe the method that we used. We drew diagonals to non-adjacent vertices and then counted the triangles. All right, so use this method you described in item 4 to answer the following. Explain how to determine the sum of the measures of a hexagon. So if I wanted to find the sum of the interior angles of a hexagon, I pick one of the vertices. So I'm going to pick this one right here, and I draw diagonals to all the non-adjacent. So this one's adjacent, this one is not. I can draw one there, there, there. Kind of starts to look like seashell design, and I have 1, 2, 3, 4. So I end up getting 720 degrees for this one. However many triangles there are, multiply each one by 180, so we end up getting 720 degrees. All right, that's interesting. Maybe we could just use this for 100-sided figure. For any polygon, seems as though we could just do the same method, right? So same thing here. For a hexagon or any other polygon, this is what we could do. So let's go ahead and do that for this table right here. We know a hexagon has 6 sides, heptagon is 7, 8, nonagon is 9, decagon is 10, dodecagon is 12. To figure this out, how many triangles could we draw inside of a triangle? There's 1. The sum of the measures is 1 times 80 is 180. For the quadrilateral, we did we got 2 triangles, and very quickly we start to realize on those pentagons we got 3 triangles. On the hexagon we got 4 triangles. Is that going to keep following that pattern? I'm going to draw one more. I'm going to draw a heptagon just to see. So 7 2, 3, 4, 5. Yep, we do get 5. Okay, so I'm going to assume that pattern continues on and go ahead and get these calculations here as well. So 900, 1080, 1260, 1440, and a dodecagon has 1800. Oops. Okay, so how could we do this for an n-sided gon? N could represent any number. Well, how do we figure out what we need to multiply by 180 compared to the number of sides? It's always just 2 less than that. So this would be 6 times 180, 7 times 180, 10 times minus 2. So we just need to know the number of sides and subtract 2. And then multiply by 180 to be able to figure this out. So n minus 2, times 180 is how we could figure out the sum of the interior angles of any polygon. And n is just the number of sides. We subtract 2 to figure out how many triangles we could draw, and then multiply by 180. Okay, so the observant item 6, that the number of sides increased by 1. The sum of the angle measures also increased by a constant amount. For every side that we added 180 degrees or another triangle. For every one side, we added another triangle or 180 degrees. So whenever we have a constant amount of change, that is a linear function. And it says for the first 6 polygons in item 6, plot the ordered pair. Okay, so let's do that. So let's say it has, and these are the number of sides. So we don't even get a polygon till here. It has to have 3 sides to even be a polygon. And let's make the other axis degrees, and let's count by 180s because we obviously know that's where it's going to start at. All right, and so for a 3-sided figure, it was 180. 4-sided, 360. 5-sided was 540. 720. 900. 1080. So I guess I could do one more. 10 was 1440 on there. So now that we've plotted all of these, it says write an equation for the line determined by these points. So if I was going to write an equation, I could do in standard slope-intercept, point-slope. The easiest one would probably be point-slope. We know that there's a constant slope of 180. And I could write in the y minus y1 point slope would be the easiest. So I could just plug in a point that's somewhere on this line, like 3, 180. So y minus 180 equals 180 x minus 3. Okay, that's one way to do it. Another way you could write this would be in slope-intercept form. And because it is linear, I could imagine that this line did continue on down here. I'm going to do it in a different color just because that's not actually on our graph here. So at 2 here, at 1 it'd be at negative 180, and at 0 it'd be at negative 360. So the y-intercept would be at negative 360. So if I was doing slope-intercept form, we could do that as well. All right, so it says state the numerical value of the slope. I've already gone ahead and done that. It says use the units as well. So the rise over run for the rise between 2 points goes up 180 and over 1. So the rise is 180. And the units would be degrees per side, because the y-axis units are degrees. The x-axis units are number of sides. So it's degrees per side. So it's 180 degrees per side, which makes sense because for every side that we add another triangle, we get 180 degrees. All right, it says the function s represents the sum of the measures of the interior angles as a function of the number of sides. Write an algebraic rule for s. So the sum of the interior angles based on the number of sides is the formula that we came up with earlier. It's we take the number of sides minus 2 to figure out how many triangles there are, and then we just multiply by 180. So the sum of the interior angles of any polygon with n number of sides is just the number of sides minus 2, and then take that value and multiply by 180. How does this rule for item 11 compare to the slope-intercept form? So how does this compared to this? Well, those are actually the same thing. If you factor out a 180 right here from each of these two terms, hey, look what you get. You get the same thing in terms of x. They just put the 180 at the front instead of at the end over here. But if x is the number of sides, you subtract 2 and then multiply by 180. They're the exact same thing. So it's the same equation with just 180 factored out of there. All right, moving down to the last section of this lesson. It says use this rule we came up with, s of n, to determine the value of s of 7.5. So we get 5.5 times 180, so we end up getting 990. Degrees on here is, I guess. But the next question says, explain the significance, if any, given that s of n represents the sum of the angle measures of an n-sided polygon. So this is the answer we get if we plug in a number, but n is supposed to represent the number of sides of a polygon. Can you have a polygon with 7.5 sides? No. So this doesn't make any sense. You can't plug in numbers that aren't whole numbers to represent the sides of a polygon. So the next question asks us about the domain. What are the possible values we could plug in for n? Well, they have to be whole numbers. So the domain is integers. And it also has to be, they represent the number of sides of a polygon, and you have to have at least 3 sides for it to be a polygon. So integers greater than or equal to 3 would be the domain of this one. You can't have 1 or 2-sided polygon, and you can't have a polygon with sides that aren't a whole number, like 7.5 on that one. How can you tell? By looking at the graph. In item 8 that the function is linear. There's a constant rate of change. And why is the domain restricted? Because the number of sides has to be a whole number greater than 3. Okay, so at this point, let's practice with the formula. For numbers 16 through 18, we're going to use this formula we just came up with to represent the sum of the interior angles of a polygon with n number of sides equals n minus 2 times 180. So pause here, try number 16, 17, and 18, and see what you come up with. All right, now that you've had a moment to try 16, 17, 18, let's go ahead and plug these in and see what we get for this one. So for 16, it says determine the sum of the interior angles 20-sided polygon. You just plug in a 20. So let's go ahead and do that. You could either plug it in your calculator here or here. It doesn't really matter because your calculator will do 20 minus 2 for you. So let's check that. 20 minus 2 times 180. We end up getting 32, a little bit better for you. In any case, we get 3240 is the total number of degrees on that one. So we should get 3240 degrees. For number 17, with 60 sides, you could plug in a 60. So Okay, so let's go ahead and type that in our calculator. So 60 minus 2 times 180 gives us 10,440 for our answer. All right, on the next one, it asks us the sum of the interior angles of a polygon is 2340. How many sides does a polygon have? So we could solve for this one, but this time we know the sum and we're solving for the number of sides. So when we plug in 2340, we're going to plug it in here and then do a little bit of algebra to solve for n. So I'm going to go ahead and erase these up. And let's go ahead and plug in here. So 2340 equals n minus 2 times 180. You need to get rid of two things to solve for n. You need to get rid of multiplying by 180, and then you need to get rid of subtracting 2. So your first step is divide both sides by 180. And you get 2340 over 180. And then your next step is add 2 to both sides. So 2 equals n. So adding 2 on the right side cancels out. Adding 2 over here, you'll get whatever these values are, plus 2. So I'm going to type in my calculator, 2340 over 180 plus 2. So let's go ahead and clear this one. 2340 divided by 180. $15 as our answer. So the number of sides of that figure would be 15. And if you're not sure if you did it right, obviously you can plug it back into the formula to check and make sure that it works. So we do get 15 for the number of sides on that one. All right, let's go ahead and do the same thing with the lesson practice, 19 through 22. Pause here and try number 19 through 22, and I'll put the answers up here in just a moment. All right, so here are some answers for 19, 20, 21, and 22. 19, does it apply for every triangles? Yes, that's the triangle sum theorem. Every triangle, regardless of what type it is, has to add up to 180 degrees. On number 20, Denisha states that if you're given the sum of the interior angles of a polygon, there's no way to determine the number of sides. Do you agree with Denisha? No, we just did it on number 18. We figured out that with the sum of the sides being 2340, we plugged it into the formula and got 15 sides. So Denisha was incorrect. Number 21 says use technology to create a hexagon, label all of the angle measures except for one, and then see if you can figure it out. So how would we do that? If I go to a hexagon that I created here, and I know 5 out of the 6 angles, how could you solve for the last one? Well, a hexagon has 6 sides, so n minus 2 times 180 is 4 times 180. We know the sum is supposed to be 720. So if I take 720 and then subtract off each of the angles that I do know, I'll be left with this one. So then we do that, 720 minus, I rounded a little bit, but we subtract each of the angles here. We get that it should be about 106.78-ish, around there somewhere. So let's check and see if that's true. Sure enough, when I find the angle measure, it's about 106.7 something. Obviously, I rounded earlier, so it's not within the nearest hundredth of a degree. But 106.7 obviously is really accurate. So if you know the sum of the interior angles and you're missing one, you can subtract all the other angles you do know to figure that out. All right, and on the last question, says all of the angle measures of a stop sign are the same. Determine the measure of each angle. Hopefully you know a stop sign has 8 sides, so we figure out the sum. Once we know the sum of the angles, we just divide it by, there's 8 of them, and they're all going to be equal. So 1080 divided by 8 congruent angles gives us each angle has to be 135 degrees, and that makes sense. If you were to draw an octagon, we do get that each angle looks like it should be about 135 degrees on there. an obtuse angle for each one of those angles. All right, that's the end of lesson 31-1 over sum of the interior angles. If you learned nothing else from this one, you should have learned the sum of the interior angles formula. This is important. Sum of the interior angles of a polygon with n number of sides equals n minus 2 times 180. The most important thing we learned here. See you guys on the next lesson.